Okay, so in the last video, we understood that if we have a quantum system described by Hamiltonian H0 with a time-dependent perturbation, and we want to understand what is the time dependence of the state, which at psi equals 0 is this linear combination of the energy eigenstates for H0, then we can use the Schrodinger equation. Here's the time-dependent Schrodinger equation that determines the evolution of the system. We said we can always write the state at time t as the linear combination of energy eigenstates of H0. We chose to do that in this way, and so our goal was to find these coefficients Cn of t. Those will tell us what our state is at time t. And in the last video, by plugging in that general form of our state into the Schrodinger equation, we generated a differential equation that determines how these coefficients Cm evolve with time. And so now what we're going to do is solve this differential equation in the case where the perturbation H prime is small. Okay, so so maybe there's a small coefficient in front of that whole term. And so we imagine that this is not going to produce a very big change in the state. So let's have a look at the general form of this equation. It's actually a bunch of equations, one equation for every coefficient. And it tells us that the time derivative of the coefficient Cm is equal to the coefficient, a sum over all of the other coefficients Cn, actually including the coefficient m, and then you've got this matrix. So this is actually like a vector equation. It's of the form Cm, let's say we just write the vector c. So it's an equation that says that the time derivative of this vector of coefficients is equal to some matrix, and I'm going to call that epsilon times m. So some time-dependent matrix times our coefficient vector again. So I'm calling everything in the square brackets epsilon times mn of t. So I'm just going to use that notation so I don't have to keep writing that entire expression in the square brackets. Okay. So if I want to write our differential equation using that new notation, then that gives me Cm dot of t equals epsilon times the sum over n of mn of t times Cn of t. Okay, and at the end, we'll substitute back in for this matrix mmn. All right, so I've written this small parameter epsilon explicitly. That would be maybe something that would be part of the definition of H prime. So we're assuming that H prime is small. And so I'm imagining that actually there's this parameter epsilon that could be maybe the strength of the electromagnetic field if it's some traveling electromagnetic wave perturbing our atomic system. But so now we have written in this way, we have a setup that's kind of similar to other applications of perturbation theory. So in this case, when epsilon equals 0, we know what the solution of the equation is. So if we actually turn off the perturbation completely, then the solution is just that Cm of t equals Cm of 0, because the differential equation says that the time derivative vanishes. Okay. So now we can use our perturbation theory method to come up with an approximation for the solution to this equation. So perturbation theory in this time-dependent case, it's just the same idea as we had before in the time-independent case. What we're going to do is we're going to write the general solution of our equation as the solution when epsilon is equal to 0 plus some correction. So there'll be some term of order epsilon, and I'll call that Cm1 of t. And then there'll be some term of order epsilon squared times some other function of time, and so forth. Okay. And so even though we're not going to be able to exactly solve for Cm of t, we will be able to get some explicit expression for these functions in the perturbative expansion. We're just going to focus on first order perturbation theory here. Okay. And so our method for perturbation theory is just to take this expression, plug it into our differential equation, and then demand that the terms at every order in epsilon would vanish. So let's do that. So we plug this expression into this equation. And what I'm going to do is just keep the terms at order epsilon. So let's have a look at the left-hand side. When we plug in our expression here to the left-hand side of this equation, there's only one term of order epsilon, and that's epsilon times Cm1 of t dot. So the time derivative, of Cm1 of t. Okay, so this is the term with 1 power of epsilon, and I'm just removing that 1 power of epsilon. And then that must equal to the term on the right-hand side of the equation with just 1 power of epsilon. And so now, because you have the epsilon out front there, then the term on the right-hand side of the equation with 1 power of epsilon, it just comes from keeping this very first term in the expansion of our solution. And so the right-hand side of the equation becomes sum over n mmn of t times cn of 0. So that is a really simple differential equation now, because it just says that the time derivative of our unknown function is equal to some specific function of time. So these mmn are numbers that we can calculate by calculating the matrix elements of our perturbation in our energy basis. And the Cn of 0 is just the information about the original state of our system. And so we can write that the solution to this equation, because it's just saying that the time derivative of one function is equal to some other function, and the solution is just that our function that we're trying to solve for is going to be the integral of that other function. So specifically, Cm1 of t, it has to be the integral of the right-hand side. And so I can write that like this. Mmn of t prime, and then times Cn of 0. And so now, in general, we could have some integration constant, and that will be equivalent to choosing the lower end of this integral. So we can make different choices for that. But I knew to choose the lower end to be time equals 0, because what I want is that Cm1, it should vanish at t equals 0. So you can see if I plug in t equals 0 to the right-hand side, then it's an integral from 0 to 0, so that integral will vanish. And so Cm1 of time equals 0 will be equal to 0, and that's what we want. Okay. Great. So now all that's left to do, so that was our solution. Okay. Um, this is the answer in first order perturbation theory. So now we can plug back in for what this matrix M is and figure out our solution in terms of the original perturbation. So now I'm just going to substitute this guy in wherever we see epsilon times M, we put in the contents of the square bracket. And so now let's write down our solution for our coefficient functions in perturbation theory. So Cm of t. So now I'm going to write the 0th order term and the first order term. So we have Cm of 0 and then minus I over h bar, sum over n, and then integral from 0 to t dt prime e to the I em minus en d over h bar. Now we have our matrix elements. And then finally, the coefficients that determine our initial state. And then we would have some terms at higher orders. So I'll write that order h prime squared. Those are terms where we're going to have 2 powers of the perturbation h prime, which we're assuming to be small. Okay, so this is our result to first order in perturbation theory. And let me just remind you how we calculate those guys. So the h, m, n, those are the matrix elements of our perturbation h prime between these energy eigenstates. So if we're going to use this formula, we want to look at what is our initial state. That will tell us what these coefficients C are. Then we're going to need to calculate the matrix elements here of our perturbation between the various energy eigenstates of the system. And we're assuming we already know what the energy eigenvalues are for the unperturbed system. And so now we know everything in this equation. And so we can use this, for example, to predict what is the probability that I'll have made a transition to some other state at some time t. Okay, so in the next very short video, I'll just do one example of that where we have just some particular energy eigenstate initially, and we want to calculate a transition probability.